Hello everyone, welcome back. Today is Graph Theory Day 6. We're going to be talking again about Euler paths and circuits. In the last video we discussed what the definition of an Euler path and an Euler circuit was, and we also talked about a method to go through a graph and instantly determine whether or not either one of these things existed. So just to recap, an Euler path is a path that uses every edge, and this is important, every edge, make sure you pay attention to that word right there, in a graph with no repeats. So you have to use every edge exactly once, and you do not have to return back to the starting vertex. So you can start in one place and end in the other. Okay. An Euler circuit is a circuit that uses every edge in a graph with no repeats, and being a circuit, it must start and end in the same vertex. All right, so you have to start and end in the same place, and you have to use every single edge exactly once. Now remember, an Euler circuit exists if every vertex has an even degree, right? So Euler circuits have all even degree vertices. Right, so this is how you can tell instantly just by looking at a graph whether or not an Euler circuit exists, right? You don't want to go through the pain and anguish of trying to find an Euler circuit if one isn't there. So make sure you check your vertices first, make sure that they are all even. If they are, an Euler circuit will exist. An Euler path exists if only, right, if only two vertices are odd. Okay, so if you go through the graph, same way you would for an Euler circuit, you go through the graph, you find the degree of each vertex. As long as you only have two odd vertices, you're going to have an Euler path. If you have any more than two, then neither one of these things are going to exist. All right. So today what we're going to focus on is actually finding the Euler circuit. Once we know that one exists, how can we go about finding it? Is there a surefire way that will guarantee you that you will find your Euler circuit all of the time? And this is going to come in handy for problems like you've seen these problems in the past, but they're going to come in handy for problems like, hey, here's a map with a bunch of bridges on it. Can you use every bridge exactly once and return back home? Or, like the room problem, or can you visit every single room exactly once? So before, what we've been doing is just kind of guessing and checking our way through those graphs. This is going to give you a systematic process that will allow you to find whether or not you can do that and find the path or circuit guaranteed every single time. All right, so this algorithm I'm getting ready to teach you is called the Fleury's algorithm. And I'll kind of read through it here. So it says start at any vertex. If you're finding an Euler circuit, you can start anywhere you like. And if you're finding an Euler path, you're going to want to start at one of the two vertices with an odd degree, right? So if it's a path, right, find one of the odd degree vertices and make sure you start there. And you also know that if it's an Euler path, you're going to start at one odd vertice and end at the other odd vertice. All right, so at least you got those two. All right, the second step is from that starting point, you're going to choose any edge that leaves your current vertex, provided that deleting that edge, right? So if you were to travel that edge, you would then remove it from the graph, right? That's what they mean by deleting, like get rid of it. And if you do that, it's not going to separate the graph into a disconnected graph. Right, so remember back at the beginning of the unit, we talked about what it means for a graph to be disconnected. All right, so as you travel an edge, right, you would remove it. If it creates a disconnected graph, you can't use that edge at that point, right? So that's what we're going to be watching out for. If we can use that edge, we're going to add that edge to our circuit, delete it from the graph, and then we're going to repeat the process from the next vertex. All right, so let me show you what that looks like here, because it's probably kind of confusing to hear about it. It's probably easier to just to see this get done. All right, so this one says let's find an Euler circuit on this graph using Fleury's algorithm, and we're going to start it at vertex A. All right, no problem. But before I try to do any work finding an Euler circuit, I want to make sure that an Euler circuit actually exists. All right, it's a reasonable request. So I'm going to go through and I'm going to look at the degree of each vertex here. So this one's got a degree of 2. This one's got 1, 2, 3, 4 edges connected to it, so it's got a degree of 4. 1, 2, 1, 2, 1, 2. And notice that every vertex is even, so there is certainly an Euler circuit here. I know for sure one of these things exists. And it says I'm going to start at vertex A. So I'm going to start writing my circuit. I'm just going to say we're starting at vertex A. right? And then you can choose. Notice that I have two edges here that I can choose from. If I were to travel from A to D, I'm going to take this edge and I'm going to delete it. All right, so I'm going to grab my white pen here and I'm going to delete that edge. All right, so now this one is gone. Okay. And then make sure you take a look at your graph. Is the remaining graph, is what's left in the graph, still a connected graph? Let me get a bit thicker of a pen here and get rid of some of that because it bothers me. My OCD, tell you what. There we go. All right, so now when I look at this thing, it is still a connected graph, so that was a perfectly acceptable edge to use. So I'm going to go back here and I'm going to add D to my circuit. All right, so now my current vertex is D, and I'm going to have to pick one of these edges. There are three edges that I could pick, and when I travel that edge, I'm going to end up deleting it from the graph. So I'm going to choose to go to, let's go to E. So grab my white pen here, and we'll delete this edge. There we go. So I'm looking at my graph right now. It is still connected, so I'm going to go ahead and add E to my circuit. All right, and now that I'm at E, I only have one edge here that I can possibly choose, so I'm going to make sure that that's the only edge I can choose. So this next edge going from E to B is the one that I'm going to have to delete. So I'm going to get rid of that one. There we go. So that one's now gone, and I'm going to add B to my circuit. Right, so A, D, E, B, and now I'm looking at my graph. It is still a connected graph here, so I only have one edge that I can delete going from B to D, so I'm going to delete that edge next. There we go. And again, it's still a connected graph, but let me go ahead and add D to my circuit. And you can see it's still a connected graph, right? Whatever remains just needs to be a connected graph. So this is what remains. All 3 points are still connected to each other. So now I've got to choose one coming from D. The only option I have is to delete this one coming from C. So I'm going to add C to my circuit, and I'm going to delete that edge. So you can kind of see what that looks like there. And again, I look at it, it's still connected, right? Whatever remains, I have my two vertices, they're still connected. So I'm gonna go from C back to A here, and that will complete my circuit. Okay, so C back to A. This is my Euler circuit. Okay, and so let's try a different one. And this one's going to be a bit bigger, guys. This is a bit bigger of a graph, so that way we can see that flurries process. Now, watching me, you might think, like, this is kind of slow. It might have been just quicker for me to trial and error my way through the graph like we have been doing, but when you get to a graph like this, that's pretty complicated. It's going to be difficult to find an Euler path or an Euler circuit if one does exist. And Fleury's algorithm does get much quicker. It's a pretty quick algorithm once you get the hang of it. All right, so I'm going to do the same thing. It says determine if the graph has an Euler path or an Euler circuit. That would be a wise choice to go through and evaluate the degrees first to make sure that one exists, because I might throw one at you that doesn't have one, and that is actually a blessing in disguise, because if I give you one that doesn't have one, all you have to do is say neither a path or a circuit exists because, and you would tell me there are too many odd vertices. All right, so we're just going to go through here and I'm going to mark these. This one's got a degree of 2, 1, 2, 3, 4, 1, 2, 3, 4. And you can see it goes really quick, right, once you know what you're doing. So you have a degree of 4 here, 4, 1, 2, 3, 4, 5. Oh, okay, so warning sign here. This one is odd. All right, so we can only have one more odd. So this one's got 4, 1, 2, 3, 4, 5. There's a second odd one. All right, so if we get another odd, we're not going to be able to do this. Okay, so 1, 2, 3, 4. 1, 2, 3, 4. Okay, 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. All right, so we are in luck. We only had 2 odd vertices, so we are going to have an Euler path here. So I'm going to go ahead and mark that down. I know we're finding an Euler path. and my path is going to have to start at one of these two vertices. Okay, so you'll notice that none of the vertices have letters or names, so I'm just going to go ahead and go through and name these. So I'm just going to go in order: A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. All right, so there we go. So we got all the vertices named, and I'm going to start my Euler path at J. Okay, so I'm going to start writing this out. I'm going to write J, and I know that this thing is going to end at G. All right, so when I'm done, I'll be at G. All right, so I'm going to grab my white pen. And again, like I said, you have options here, right? So we've got 1, 2, 3, 4, 5 edges that we could choose to start with. I'm going to go to K first, so I'm going to delete K. Or this edge that goes from J to K, I'm going to get rid of that first. And then I'm going to add K to my path. There you go. Once I'm at K, I'm going to pick another edge. And just making sure that as I delete the edges, I'm evaluating whether or not this graph is still connected. This graph is still connected even after I deleted this one. All right, so the next one I'm going to go to L, so I'm going to get rid of this and add L to my path. All right, then we would do the same thing. So going from L, I'm going to delete up to H. And then I'm going to go from H to D. And you might choose to go a different way with this. You might not go the exact same way that I'm going here. All right, so I'm going to add D. All right, so I went J, K, L, H up to D. Now from D I only have one option, so I have to go to C. So I'm going to go ahead and add C to my path. Like I said, you're going to get going pretty quick. The only mistake that students tend to make with this one is just not checking whether or not it's connected. All right, so again, I'm just kind of always looking through, making sure that I don't have any disconnected segments of the graph here. Okay, so everything that remains is still connected. All right, so we went from D to C. So from C, I'm going to go to B. Let's just work our way across here. And stay systematic and organized with it. So make sure that you're marking your path as you go. All right, and then from B, I'm going to go to A. So once you get the hang of this, it goes pretty darn quick. Get my pen back here. All right, so I'm at A. I only have one option. I got to go down to E here. Dash. There we go. Add E to my path. AE, so I'm going to go from E to I. So I'm just going to work my way around the outside. Because right now I'm doing pretty good staying connected, right? So if I'm looking at what is remaining after I've deleted stuff here, you'll see it's all still connected. So I'm just going to work my way around the outside, I think. Keep that as my strategy for now. Okay, from I, let's go to M. I don't think that will cause any problems. Go. And then from M, I only have one option. Okay. I have to go to N. Now at N, I do have three options here. Let's see, I'm going to go to O. I don't think that's going to create any issues. Even if I get rid of this, we're still connected up here by this segment, so this side of the graph will still have access to this side of the graph through FG. All right, so as we start deleting more and more things, we got to be more careful about where we're at. Okay, so just again, make sure you're double checking the connectedness of your graph as you go through, right? So we're going to go from N to O, and I'll add O to my path. Okay, so now I'm at O. I have options here, so let's see, let's go to P. Just keep working our way around the outside. That's been working for us so far. Okay. Okay. Then from P, I only have one option, so I'm going to go up here to L. All right, we're still good, still all connected. Got to go to O. All right, then I only have one option from O, so I have to go up to K. And then from K up to G. Okay, still all connected. And then let's see, L, O, K, G, H. All right, so let's go to H next, and we'll kind of work our way around. If I delete this triangle in sequential order, I shouldn't have any problems, right? So I'm going to delete this edge, then this edge, and that should keep it connected. So I'm going to do a little bit more forward planning here just to speed this up, right? So I'm going to go G, H, C. So I'm going to add those two. So I'm adding edge GH and HC to my path here. I can do a little bit more at once here, right? So I'm getting rid of this edge, still connected, and then this edge up to C, right? It's still a connected graph. And then I'm going to go ahead and get rid of C to G. Okay. Then I'll add G. All right, and then let's see, so CHG. So at G, let's go to F. Okay. There we go. So again, I'm still connected. I can get to every single point. There's no disconnected pieces here. So then the next one, going from F, I'm going to go up to B. So I'm going to delete the triangle, kind of like I did with the one over here, right? So I'm going to go B, E, back to F. So I'm going to say B, E, F, and go in that order. Okay, so we go up to B. I'm deleting that edge. Still connected. Then going from B to E. We're still connected. And then from E to F. Go. And then I only have one option, so I have to go from F to J. So let me add J to my path. Grab my pin. And we'll go from F down to J. Okay, so I think the strategy should be here is to go around this triangle just like we did the other ones, right? So if I go around, I'll be back here at J, and then I can get back to G, which is where I need to end. So I can see the rest of my path here. So I'm going to go ahead, I'm going to go J, I, N, J. And I'm going to continue this down here, J, I, N, J, and then back to G. All right, and we'll delete so that you can see the whole thing in its entirety here. I think it's pretty obvious how this is going to go, right? So J to I, again, everything is still connected. And then from I to N, everything's still connected. And from N to J, right, that's this edge right here. And then from J back to G. And at no point did we ever create a disconnected graph to create that Euler path. Okay, so that was kind of a lengthy one, and I needed to show you a lengthy one so that you saw the value of that algorithm, because trying to find that Euler path without an algorithm would have been extremely difficult. It would have been very difficult for you to kind of, guess your way through that and try and just find it without any procedural context, okay? And like I said, watching me, it feels kind of slow watching me, but when you're doing it yourself, you're going to be able to move much quicker, and you won't hear me explaining like every little move that I make. So you'll be able to go much quicker than what you saw here in the video. All right, so don't get discouraged. It's not going to be a super long problem all the time. All right. So let's go down here. Once you guys on your notes, I want you to try this one on your own. All right, so I'm going to go ahead and write down. I'm going to write down what you should find here. Right, so if you go through and you analyze all the vertices, you're going to notice that they're all even. So you're going to have an Euler circuit that you're trying to find here. And if you're wanting to check yourself, I'm going to start my circuit at A. Okay, and I'm going to name my vertices like this. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, and O. Right, and we're going to be starting up here at vertex A. This is where I'm going to start my circuit, and since it's a circuit, this thing is eventually going to come back home to A. All right, so what I want you to do at this point, just pause the video, give this one a try, see if you can find the same circuit that I do, and check yourself as you go. Okay, and I'll write out the circuit here. When you push play, you'll see the entire circuit written out, and then you can check and see if you got the same circuit. You probably won't, because there's a lot of different options as you go through this, but you'll have at least one correct circuit here for you to check.